Hello everyone. Today we are presenting a CIRRUS, a serverless framework for an end-to-end ML workflow. This presentation is presented by Prashant, Pranav, and Ankita, myself, under the guidance of the Professor Christian Borsia. Uh, these are the corresponding author who had represent the CIRRUS and the ML workflows. And this is the outline we are discussing today, like motivation, design, implementation, evaluation, and conclusion. So first is the machine learning, like ML. ML is a method of the data analysis that automates analytical model building basically branch of the artificial intelligence based on idea. The system can learn from the data, identify the pattern, and make the decision with minimal human intervention. Machine learning identifies the different object from a single input image. For example, when an image of a cat is supplied to the algorithm performs and curl steps over an images. First is the classification. In this example, the algorithm is trained in such a way that whatever it be, single object or a multiple object, it identify it as an individual object like cat, dog, or a duck. Now the complex ML workflow for Amazon SageMaker. So ML workflow provides the ability to build, train, and deploy the machine learning models. So that workflow consists the three heterogeneous stages: data preprocessing, model training, hyperparameter tuning. So for data preprocessing, we classify the data and then send to the training for helps in the ML workflow, and tuning the algorithm based on the parameter. So the ML workflow are repeatedly executed by the user but have the heterogeneous computational requirement. ML workflow are interactive and iterative. This complexity of workflow makes it challenging of ML user to correctly provision and manage the resources. Over provisioning. So the over provisioning is the heterogeneity of the different tasks in ML workflow leads to significant resource imbalance during the execution of training workflow. For like instance, the course's granularity and rigidity of VM-based cluster as well as the design of the ML workflow. Developer can go back and forth between different stages of the workflow to experiment with the ML parameter. Hence, the over-provisioning was the first that we faced during the traditional ML workflow. Now let's begin with the explicit resource management. So for explicit resource management, we exposing the low-level VM's resources and put a significant burden on the ML developers. So there are some challenges of the provisioning, configuring, and manages the resources for each of the ML workloads. It requires user to perform a task, and in a practice, over-provisioning and explicit resource management burden are tightly coupled. Now, as you have understood how tightly coupled it is and how it increases the burden on developers, a system is developed and approach is applied to address this resource provisioning challenge by using serverless computing. However, the serverless computing has limitation. The first one is a small memory and storage. AWS Lambda can only access 3 GB, 3 GB RAM and 512 MB of local disk. The resource limitation prevent use of any computational framework. The second one is the low bandwidth and lack of peer-to-peer communication. The largest AWS Lambda can only sustain 60 MB of bandwidth, which is lower than 1 GB of the bandwidth, is available in the medium size of VMs, as well as the serverless computing units such as the AWS Lambda do not allow the peer-to-peer communication. So the third limitation is the short-lived execution and unpredictable launch time. It takes to several minutes to start after being launched, unpredictable time, and can finish in the middle of the training. And the last limitation is the lack of the fast storage. So for that, high latency and low throughput and not optimized, because the Lambda function cannot connect between themselves. Shared storage need to be used. As of today, there is no fast serverless storage for the cloud. So till we have discussed what are the problems we faced in existing traditional serverless computing and the end-to-end ML workflow. So let's understand what is the proposed solution provided by the CIRRUS. It automates the end-to-end management of data center resources. It eliminates the manual resource management workflow, and it combines the simplicity of the serverless interface and the scalability of the serverless infrastructure. It helps to minimize the user effort, and it addresses over-provisioning and user productivity and the model effectiveness. It enables to ML training workflow and the algorithms, and it also performs the scalable ML training leveraging the high scalability of the serverless environment and the cloud storage. So now the design part will be explained by the Pranav.
Hello everyone. CIRRUS is an end-to-end framework specialized for ML training in serverless cloud infrastructures. It provides high levels of primitive to support a range of tasks in ML workflows. The design principles that CIRRUS provides are the adaptive fine-grained resource allocation. In this, to avoid the resource waste that arises from over-provisioning, CIRRUS flexibly adapts the amount of resources reserved for each workflow phase with fine granularity. Second, the stateless server-side backend. To ensure the robust and the efficient management of serverless compute resources, CIRRUS by design operates a stateless server-side backend. Thirdly, end-to-end serverless API. Model training is not the only important task an ML researcher has to perform. Dataset preprocessing, feature engineering, and parameter tuning are other examples of the same. These tasks equally are important in yielding the good models. The fourth part is the high scalability. The high scalability in the CIRRUS provides efficient parallelization for computing the intensive ML programs. CIRRUS should be able to run thousands of concurrent workers and hundreds of concurrent experiments. Now let's understand the system architecture that the CIRRUS is built on. CIRRUS uses three building blocks. First is the Python frontend, which is developed for ML developers. This includes the client's front-end part and the client's back-end part. The second is the data store, that is the serverless storage that CIRRUS provides. And third is the worker runtime on which The CIRRUS runs the serverless run lambdas. Now let's understand the client-side architecture of the CIRRUS. CIRRUS consists of a stateful frontend which coordinates worker through the data store to overcome the P2P, that is peer-to-peer communication challenge. The client side contains a user-facing front-end API and it supports pre-processing, training, and tuning. The client-side backend manages the function which are provided by the cloud and the allocation of the task to that function. The front-end API, which supports pre-processing, training, and tuning, the pre-processing includes the submodule which allows the user to pre-process the training data sets that are stored in the S3 model. The CIRRUS training submodule allows the ML models that can be trained with a stochastic gradient descent. Currently, CIRRUS supports the sparse logistic regression, latent Dirichlet allocation, softmax, and collaborative filtering. The third part is the tuning. The tuning involves hyperparameter optimization. The hyperparameter optimization allows us the users to run a grid search over the given data set of parameters. The Python front API and the client frontend. The API is totally contained within the Python package. The API provides a high level of interface that abstracts the underlying system level resources. The user interface through which the developers can visualize progress of their work. Hence, the client-side Python frontend consists of these three main tasks, that is pre-processing, tuning, training, and it also provides a user interface through which the developers can visualize the same. Now let's understand the client-side backend of the Python frontend. The Python frontend is an interface to CIRRUS client's backend. This backend performs a number of tasks. First, that is, it passes the training data, it loads that data to the S3, and it launches the CIRRUS workers on lambdas. Secondly, it manages the distributed data store, keeps the track of the progress of the computations, and returns the result of the Python frontend. It also consists of a low-level scheduler which has the responsibility to launch, kill, and regenerate tasks. It keeps a track of all the states of the system. Now let's understand the server-side architecture of the CIRRUS. The server-side architecture consists of three parts, that is the client-side backend, the worker runtime, and the distributed data store. In the client-side backend, it consists of the Lambda workers and the data store. The Lambda workers exports the data iterator API. It contains efficient implementation for the iterative training algorithms. The data store stores the gradients, the models, the intermediate pre-processing results. Now let's understand the next block that is there in the CIRRUS building blocks, that is worker runtime. CIRRUS provides a runtime that encapsulates all the functions that are shared between the computation system. The system runtime meets two goals. The first is lightweight and high performance. How does it maintain lightweight? It runs within the memory constraint lambdas, like the lambdas are being constrained by the memories. The second one, the high performance, it mitigates the communication and computation overheads exacerbated by the serverless infrastructures. The worker runtime provides two interfaces. First, it provides a smart iterator and for the training data sets that are stored in S3. This iterator prefetches and buffers many batches in the Lambda's local memory. Second, it provides an API for the distributed data store. This API implements data compression, sparse transfer of data, asynchronous communication, and sharding across multiple nodes. Now let's understand the next module or the next block of the CIRRUS, that is distributed data store. The CIRRUS data distributed store serves the purpose of storing the intermediate data to be shared by all workers. The storage for serverless Lambda needs to meet three goals. First is the low latency, that is, it should have a latency of less than 300 microseconds. Secondly, it should be able to scale to hundreds of workers to achieve a linear scalability for the infrastructures which are serverless. Thirdly, it needs to have a rich interface to support different ML use cases. For instance, it is important that the data store supports multi-jet, general key value pairs, put get operations, and a parameter server interface, that is an interface which has parameters from the server. To achieve low latency, we deploy our data store in cloud virtual machines. It achieves latencies as low as 300 microseconds versus 10 milliseconds for the AWS S3. Now, to achieve the high scalability or the linear scalability, Cirrus includes the following mechanisms. The first is sharded stores, highly multi-threaded, the data compression, the gradient filters, and the asynchronous communication. These were some of the serious building blocks that we need to understand before we understand the implementation of how Cirrus performs. Let's now understand how end-to-end ML workflow stages perform. This section describes in detail the computation of how Cirrus performs. It consists of three stages in the process after the data is obtained. As discussed earlier, those three stages are data loading and pre-processing. The second is the model training, and third is hyperparameter optimization. Now let's understand what data loading and pre-processing is. In data loading and pre-processing, the deserialization of the dataset happens. That means when the data is being transformed or uploaded into the S3 bucket, it is transformed into from the original format to the binary format. The original format is the CSV file of the dataset. The next thing is partitioning of the dataset. The dataset is usually partitioned in the similarly sized partition. The third one is the phases to achieve performance. How do we achieve a low latency in the data store? In this, we implement map phase and the reduce phase. In the map phase, each worker computes statistics for its partition. In the reduce phase, these local statistics are then aggregated to compute the global statistics. After these two stages are performed, a final map phase is done where the workers can transform each partition sample given the final per column statistics. Now hence, for large data sets, the map and the reduce phase aggregates per column statistics which generates a large number of new writes and reads per second beyond the transactions throughput supported by the SA. Hence, for this reason, we use Cirrus's low latency distributed data store to store the intermediate results of the map and reduces. The next stage of the end-to-end ML workflow are the model training. In model training, the Cirrus uses a distributed SGD, that is stochastic gradient descent algorithm, for the model training. Workers run on Lambda functions iteratively to compute the gradient steps. Every gradient computation requires two inputs. The first one is mini batch and the second one is an up-to-date model. The mini batches are fetched from the S3 through the Cirrus runtime iterators. Why do we fetch it from the iterators? Because these mini batches work within the worker's memory, and it also has a very low latency. The most up-to-date model is retrieved from the data store using the data store API because it retrieves every mini batch synchronously from every iteration of worker computes. A new gradient. This gradient is then sent asynchronously to the data store to update the model. Now let's understand the third stage and the final stage of the end-to-end ML workflow. It is called as hyperparameter optimization. The hyperparameter optimization is basically a grid search based on the model parameters, which helps in yielding the best accuracy. This grid search may be brute force or adaptive. The API and the execution backend for launching and hyperparameter search. Then the second one is the dashboard for monitoring model accuracy convergence. And the third one is the ability to terminate individual tuning experiment and save on the over provisioning cost are the three main features that Cirrus offers. So these were the basis of the designs implementation that was done on Cirrus while understanding the problems that were faced in the traditional systems. Now let's understand the implementation part from Prashant.
Hello friends. So till the time we have understood the motivation and design part, now we are going to see the implementation part. So basically implementation is composed of four components. The first one is a Python front end which is developed in Python. The second one is a client backend which is also developed in Python, and distributed data stored and worker runtime both are developed in C++ for efficiency. So let's see client frontend and backend implementation. So Python frontend uses a thin Python API that overrides the Python internal configuration. Then there is a UI running on a plotly. So basically plotly is a graphing library which is provided by Python. Then UI for frontend also provides a monitoring the progress of workloads and the tasks like start and stop. The client backend lists the currently active lambdas. Then it also provides the list of connections to the Lambda AWS API. Also, it automatically activates and relaunch the lambdas. So that are the implementation. Let's understand the implementation of data stored and worker runtime. So in distributed data store, an interface is provided which stored and intermediate data in the ML workflow. Then interface also supports a key value and parameter server interface. It also uses a multi-threaded server with multiple core utilization and data compression. In the worker runtime, it provides a set of linear algebra routines to calculate the linear calculations. It also provides eigen to reduce serialization and deserialization. Also, it has a mini batch based iterator for low latency. So this is everything about the implementation. Now let's see the evaluation. For evaluation, it runs a serverless system, CIRRUS and parent on AWS Lambda. In all experiments with the serverless system, the training dataset was stored on AWS S3. For deployment, it uses AWS Lambdas with 3 GB of memory. As a benchmark, it uses asynchronous distributed SGD sparse logistic regression task. Also, the dataset is uses Criteo dataset. It is a dataset of displaying ads. Also, as a baseline, it uses Pyren, which is iterative synchronized SGD training using AWS S3 to store gradients and model. Also, it as a baseline, it uses 3 plus 3 incremental optimizations. The CIRRUS will set up in two different modes. One is with prefetching and another is without prefetching. As a part of evaluation, CIRRUS sparse logistic regression implementation compared against two specialized framework for ML based ML training. One is the TensorFlow and another is Boson. So TensorFlow is a general purpose data flow engine used for ML computations. Boson is a distributed and multi-threaded parameter server. So from that sparse logistic regression, CIRRUS achieved a logistic test loss over time with varying number of servers. Then it also reaches the best loss, or the TensorFlow achieves 3.75 faster. It also converges faster and achieves a lower test loss than the Spark. So now let's understand the storage scalability. Finally, the scalability is an important property for ML workflow. So we show that the choice of serverless infrastructure rests on its impressive scalability. So CIRRUS scales linear leveraging that can be accomplished by designing the system to scale across three dimensions. The one is storage of training data with S3, that is storage scalability. The second with compute with lambdas, and the third is shared memory with a distributed parameter server. Let's see the storage scalability. The CIRRUS addresses this issue by splitting training dataset in S3 into a medium-sized objects. It uses 10 MB objects because this size achieves good network utilization while being small enough for even the smallest size lambdas. Also, by using large objects, it reduces the number of requests per second. As shown in graph, it achieves the ideal linear scaling from number of worker 1 to the number of worker 1000. So the worker consumes 30 MBs of training data. Also, as a result, this, we are able to scale S3 throughput linearly to thousands of CIRRUS workers. Now understand the compute scalability. The challenge for the compute scalability is to run a large number of workers that perform a compute intensive operation such as computation of model gradient. The CIRRUS workers can scale when the training data set is backed by S3 with no synchronization of models and parameters. Also, CIRRUS can achieve linear compute scalability by streaming the input of a training data and computing gradients in parallel. So, as per graph, the number of workers can scale from 1 to 100 against the gradient. For each worker, it consumes 30%, so 30 MB of training data per second. Let's understand parameter server scalability. At the parameter server level, the main challenge arises from the limited network bandwidth of each VM. Also, the compute required to update the model and at the same time serve the request from the workers. So CIRRUS solved this problem with different components like model sharding, then sparse gradients or models, then data compression, and the last one is asynchronous communication. So CIRRUS achieves linear scalability up to 600 workers to achieve the parameter server scalability. As shown in graph, the CIRRUS achieves the samples per second with the number of workers scale from 1 to 600. For this also, the worker consumes 30 MBs of per second training data. Let's understand the ML specialization evaluation in the next slide. So to evaluate the advantages of a specialized system for ML, we compare CIRRUS against Pyrene. So Pyrene is a MapReduce framework that runs on a serverless lambdas. So it provides a primitive that scales to thousands of workers. Also, the primitives used to implement algorithms such as large-scale sorting, data queries, and machine learning training. So Pyrene is optimized with help of its runtime to run on AWS Lambdas. For this evaluation, CIRRUS implement a set of optimization with Python as a baseline implementation. The same serverless platform we use for all CIRRUS experiments. So each Lambda invocation executes a multiple SGD iterations and asynchronous SGD. The the mini batch prefetching and sparse gradient is used as a part of optimization. Also using a low latency store with the help of Redis instead of S3. Based on this comparison, let's understand the Python and CIRRUS performance. So to calculate performance, we check on a sparse logistic regression workload when running on 10 lambdas. So as shown in the graph, the CIRRUS achieves 2 orders of magnitude more than model updates. It also uses the combination of prefetching, reusing lambdas across the model training iterations, and efficient model sharing through the CIRRUS fast data store. Also, the training data prefetching masks the high access latency to S3, which results in an additional 10x more updates per second. So all these experiments and results shows how CIRRUS is beneficial as compared to the traditional workflow. So from whole presentation, let's understand the conclusion. So as we've seen, the CIRRUS has provided outperform existing serverless solutions by specializing for a serverless and ML. So the problem with traditional workflows are infrastructure management, and it's a time consuming for developer. Also the resource over provisioning is one of the important problem. So CIRRUS simplified it by using the simplified deployment of ML workflows. Also it provides a per stage provisioning of resources. Also CIRRUS provide transparent serverless resource management, scalability, and fault tolerance by its design. So overall it outperforms the existing serverless solutions by specializing for serverless and ML workflows. Thank you.